Okay, can you all hear me okay?
Yes.
All right, I wanted to tell you everyone that first I want to get through some stuff, get rid of that, and we'll talk about the quiz. The first thing I want to say is that if you have an excuse and you missed the prior quiz or any other quizzes, what we're going to do is have a group quiz session, and you'll need to bring your excuse, and I'll announce that later once everybody is over this COVID-19 or any other or whatever problem you had, and it'll be a collective thing that will be probably in a week or so that we'll take. And I'll announce that, but there are people that still can't take it. So if you missed the quiz, have an excuse, then you will take a collective makeup at that time, and I'll announce that. I still have a bunch of people that are out. During the quiz, we had, I believe it was 77 students that showed up out of 93. I'm not exactly sure, 75 or 77. And that's a remarkably low number. I've never had that low number. So we'll make amends for that. Now, all the quizzes will be on campus, and they will be at either in Brown Hall or Brown Koppel, and that will be introduced. You cannot take a quiz via Zoom unless this university shuts down. Is everybody clear on that? I don't see anybody with a camera on. I don't know if it's me or if it's you.
Yes.
All right, if you want to turn your cameras on, it helps. Now your quiz grades are up there, I believe. Are you able to access Canvas and see your grades? Just any kind of affirmation would help.
Yes.
All right, thank you. And if, okay, good. I'm glad to see that. The second thing I want to tell you is that my grader and myself, primarily my grader, have been working with the Biggio Center to try to get your first quizzes that were taken online uploaded to Canvas. I apologize for this. I still don't know what the problem is. Is my grader on here right now? Chun-Li, are you on there? I can't see your name, and there's too many names. Well, anyway, we're doing our best. Hopefully today we'll get them uploaded. People have asked about them. Now, he sent you a message. Did everybody get a message? It just was out a couple of minutes ago, an email. It's the first time I had absolutely nobody besides myself on camera.
You got the email, Dr. Baginski.
All right, if you got the email, it should detail his room and his availability to give back your last quiz. Do you all see that?
Yes.
Okay.
Yes, sir.
All right, I'm doing my best here. This is an odd feeling when I cannot see another person. You really don't know who you're dealing with. Now, hold on. Over here is the quiz. Can everybody see the quiz?
Yes, sir.
I'll put this in OneNote. If we take a look at the first problem, this was meant to be just a very simple problem. There is nothing tricky about this. And I got to say one other thing. If you took the quiz, you don't get a retake. If you took the quiz, you don't get a retake. But if you didn't take the quiz and have a legitimate excuse, you get a retake. I wanted to get that out of the way. So the first quiz, I asked you just for V0. Y'all see that? People?
Yes.
All right. Now, I'm just asking for a little participation so I can deliver this lecture as best I can. I really am struggling here. I would rather not have us meet on campus every day, but if need be, I'll do that. I'll have everybody on campus every day when we meet. And I've been given permission to do that by the provost's office if this becomes too difficult because of the size of the class. But if we look here for V0, now this is a standard question. You can do it any way you want. It doesn't matter what you do. Here, it's the simplest thing. Look at the negative point where V0 is, and you simply go around. That's an increase of 12. That's a decrease of 6. And that means V0 would be 6 volts. Does everybody see that? Just some affirmation. If you do, or if you don't, let me know. I'm hoping you all do. This was meant to be trivial. By the way, I understand quiz grades are much higher. I don't have them in front of me. If my graders here can tell me what they were, but they were much higher, and I'm glad for that. So that was one of these things, just a sanity check. If you know what you're doing, this takes but a second. If you don't know, it's evident. People try all sorts of things, and you can do this many ways. For instance, if you just take this, if you did Thevenin, if you remove the actual load, right? So you remove 1K right here. Can you all see my cursor too, by the way?
Yes, sir.
All right, if you can see my cursor, if you remove 1K, we all agree that's the load, right? Because that's where the unknown quantity V naught is. If you remove it, the next thing you're going to do is find the open circuit voltage, which would be 6 volts. The next thing you do is find the short circuit or the Thevenin resistance, right? The Thevenin resistance, we turn off the sources. So these two voltage sources would be 0, correct? There would be just short circuits, and R Thevenin would be 0. Therefore, you would have 6 volts in series with 0 ohms, and put back the load, you get 6 volts as the load. If you did it that way, but it doesn't matter which way you did it, you'll get the same answer. Are we clear on that one?
Yes.
Any problems or questions about this? The second one was, this is the one you saw coming, and thank God a lot of people got this right. Here, we have 2 loops. There's no tricks here. Not a thing. This is right out of the book, literally out of the book. If we come around the first loop, now I call this I1, right? And I can write this if you want me to. If you take a look at this, first as I'm going around, you see we'd have -4 volts, right? Agree, class? If you go around the first loop as I'm showing you, you would run into -4. Agreed, class?
Yes.
Then you would run into what? I'm going to put -8K right there because I know I'm going to have I1 times 4K and I1 times 4K here. You all see this? Some of you are up. So
Yeah.
it's -8K times I1, right? And maybe I should do it this way. And then you would have plus what? 4K, right? Times I sub 2, right? Hold on. I got to stop the party. Who else is talking? If you see somebody that's talking, let me know so I can just focus on. So this would be equal to 0, correct, class? That's the first equations right here in the first one. Does everybody first agree with that?
Yeah.
Yes.
Any question about this? This is a very, and I went through it kind of quick, but you could start here. It'd be -4K times I1 minus I2 -4 volts, right? And then -4K I1 minus, -4K just I1 -4, and then -4K I1 minus I2 equals 0. But if you break it down, it'll come down to this. That would be a first equation. Second equation is around here, right? This loop. Y'all see me?
Yeah.
Now I'm going to put the 12 first. So it would be it'd be plus 12, right? It would be an increase. Sorry, it would be plus 12. That's here. I'm putting the voltage first. Doesn't matter where you start. If I start here, plus 12, then it's going to be what? -4K. And let me go down here with this. -4K. And then it's times I2, but you'll notice there's going to be a -4K here and then another -4K. So I'll just make that -8K, right? Right? And then over here, I can see it would also be what? Plus, I know I'm going to have a plus 4K I1, correct, class?
Yeah.
Mm.
And equals 0. Those are the two equations the grader's looking for, and then these two equations you would simply modify to get in a matrix form. So you would take the -4, pardon me for having this thing jump like this, the -4 to the other side, plus 4, the plus 12 to the other side, -12, correct, class?
Yeah.
You understand this is just standard linear algebra manipulations. Then you would divide through by 4K. which would mean the coefficient of I2 is 1. The coefficient of I1 was -2, right? This is this. And then over here, you would have simply what? Plus 1 milliamps. And that's this B vector here. B is a column vector, 1 milliamp. The second one, you would take 12 on the other side, minus 12. Then you would divide by 4K, which means the coefficient I1 would be 1, which is right here for the second column, right here, the 1. Then you would have the coefficient of I2 would be -2, that's here, equals 0. You'd go through and get this, and there would be your solution. I used Octave to do this. Is everybody following me? You can use your calculators to do these kind of things very easily. Correct, class?
Yes.
You all got that,
Yes.
right?
Yeah.
I'm trying to move quickly, but I don't want to leave anybody behind. Now, finally, when you have that, if I want V naught, it would just simply be I2 times 4K. Do you agree with that?
Yes.
Yes, sir.
Or it would be 4 times 1.667 or 6.667 volts. Agreed? Agreed?
Yes.
Yes.
And that's the essence of this. It was a very direct quiz. If you did the homework and understood it, you probably did very well. And I must say, I didn't look at in detail at this, but I understand that the grades were very high, even with the zeros for people that I guess didn't have a legitimate excuse or however they were calculated. So I'm glad about that. Any questions before we move on to the next topic? These questions can include Thevenin, Norton, nodal, superposition, I'm sorry, not superposition, mesh, and any other questions you had about resistances, combinations, either in series or parallel. Anybody at all? I'm trying to figure out how many we have here. We got 80 participants. Okay, good. Are we good?
Yes.
For the makeup quiz, will it just include the things that were on this quiz, or it's not going to include like things we go over today, right?
Well, the makeup quiz is going to be directed at mesh and nodal and Thevenin, right? It's all the stuff we've covered up to the point of the quiz.
Okay.
All right, but I mean, if I were you, I would, you're going to see how all these things naturally apply to what we're about to do. There's no breaks in the action. Everything is just built upon the prior stuff. Okay, whoever asked that. Fair enough?
Yep.
Okay. Next thing I'm going to do is start talking about what I'm going to term, this is going to be time varying phenomena, but what I want to do is talk about steady state time varying phenomena. And this is going to be something that we term as AC or alternating current type of behavior. And I want to do this. Here's what I'm going to do. I'm going to shut this down for now. And I'm going to bring up the doc cam, hopefully. There we go. And can you all see this okay? And some people are going to ask me, or at least I think it's fair to assume some of you would like to see a reference to this book, which is a legitimate request. I don't generally use textbooks when I teach. I mean, I'll reference problems sometimes, but when I teach, I don't use that. Now, his book is going to have a lot of stuff in there that is kind of overkill, in my opinion, that you don't need it. But I need to talk about a few things. And he goes through some stuff right off the bat that's a little disconcerting. Now, first, I'm going to say this. On page 41, he has the DC mode. Now, DC simply means direct current, or it doesn't vary with time. Can you all see this, by the way, what I've got up here? This is on page 41 of the book, textbook that's for the course. Everybody?
Yeah.
Yes.
All right, now somebody asked about the quiz this week. Let me get to that at the end, all right? Seth, just so I'm aware of it, you can yell at me 5 minutes before or remind me 5 minutes before the end, but I want to get through this. Now, if there is no time varying phenomena, then remember, y'all had inductors, right? Remember the word inductor from physics, correct, class?
Yes.
Inductors are nothing more than some, I call it a coil of wire, something that has magnetic energy associated with current flow through it. That's the only thing you need to know. An inductor is usually shown as a coil of wire where current flows. Now, magnetic energy, when it's stored in there, can also be gotten out, but it cannot be dissipated. Likewise, a capacitor can store electrostatic energy, but it cannot dissipate electrostatic energy, an ideal capacitor, that is. How many remember the terms capacitor and inductor? Just any acknowledgement at all is useful. A hand, a head bob, anything. And if you, I mean, if you don't
Yes.
want to show your face, it's fine with me too, but it helps with a thumbs up, something that tells me you're alive. That there are more than pictures that good. I got some. Because you don't realize if you ever try to do this and there's absolutely no response, you think you're talking to the wall. And it's an irritating feeling. I don't care if you got friends over. I really don't care as long as you mute this so I don't hear them yelling. All right. Now, getting back to this. This is the equation right there for the voltage across an inductor. How many remember that? LD IDT was the voltage across an inductor from physics. Anybody? Y'all remember that? No? Okay, one person, maybe two, 2.5. That's a wobble, not a bob. That's a nod, and this is a wobble. Like, I don't know. All right, LDIDT is the voltage across an inductor. CdVDT is the voltage across a capacitor. These are two things I'm going to talk about, and then I'm going to do something that involves steady state behavior, all right? First, I'm going to do steady state behavior because it makes more sense. Now, and I'm going to try to do this in a way, here I slow down, that's as clear as possible. Now, you all know that a battery looks like this. You don't need to write this down, just listen to me. A battery is symbolized like this. We know what batteries look like, car batteries and such. It's got some voltage. Car battery is 12 volts, right? If we took a look at this and put a resistor here of, say, 12 ohms, then we would have a current I of 1 amp, right? V over R. And if we've graphed any of that versus time, either the voltage across the resistor, it would just be 12, or the current or anything, there would be no time variation. Do you all agree with that?
It hasn't focused yet, Dr. Brzezinski.
Oh, thank you. And don't be afraid to tell me things that I am not aware of. Come on. There we go. All right, that's what I'm trying to get at right there.
There we go.
It does not vary with time. Now, most of you know that the wall voltage that you have in your house or apartment varies.
Wait, Dr. Brzezinski, can you go back up? I missed that first drawing.
You're not missing much. That's a battery in parallel or series. They're the same thing for a single thing, right? With a voltage source. I'm just trying to show you that if you looked at the voltage here, V of T would be a constant. The current I would be a constant, right? It would just be 1 amp. There would be no time variation. Good? Okay, everybody knows this, don't you? I mean, a battery doesn't change with. Now, when you talk about something that is from your wall voltage, that's called AC. It means alternating current, but AC really is encompassing anything that is time varying and periodic. That's what the term really infers. So if you looked at the voltage from a wall outlet, if you had two things like that, and then I usually got a ground here, this would be plus, this would be minus. And if you would look at the voltage here, V of T from a wall outlet, and I'm just trying to show you this is what it looks like if you plug in an extension cord. Then if you graph that versus time, you get this. And this voltage here could be described as some V naught times cosine of omega T plus some phase angle. Now this is time. This would be the peak value, which would be V naught. Omega, some of you remember this is 2 pi f, right? The frequency here is in hertz. If I'm going a little fast, I'm assuming you've been exposed to this in physics in your everyday life. How many know that frequency in hertz, I mean, frequency in hertz, it's really, it's per second, right? How many cycles, how many periods per second? How many understand that, right? Y'all understand that, class? Right? Thumbs up, any kind of indication of positive. Y'all remember that, right? I'm going to assume you do because this is standard knowledge. You get this even in high school. Frequency is something that tells you how many cycles, how many 360-degree transition occur. This is the voltage versus time. You could also graph it versus angle if you want, but it's better versus time. I'm going to just say a few things. When you take a look at this, there's something called the period, right? It's the time over which it repeats itself. It's labeled cap T. This is the period. This is not going to be important, but it helps to give a bit of context. Do y'all remember that, class? Period of a waveform is the time over which it repeats itself, right? How many remember that? Physics or math? I mean, anything. And you know that frequency too, the actual frequency of this thing is a constant. Might as well call it F naught, and that's 1 over the period. And the units to this are hertz. So 1 over seconds is hertz. Y'all remember that? I believe the name came from Henry Hertz, a famous scientist. Now, when I put omega here, does anybody remember the units of omega? Anybody? Mechanical or aero should get this. Anybody?
Radians per second.
That's right, radians per second. Radians is a measurement of an angular measurement, right? It's either degrees or radians typically. Radians per second is a frequency. And that's what this is. You're going to see omega all the time. Okay? I hope I'm getting through to you. And I am assuming you did have physics, and I am assuming, at least when I say a wall outlet, I don't have to explain everything with pictures. It's where the extension cords go. Now, having said this, I'm going to talk about this for now. Let's get rid of this phase angle for now. It just complicates things. You all see that the peak value V naught would be here. When the cosine of omega t, when omega t is 0, cosine of 0 is 1, and it would be V naught. It'd be right here. Agreed, class? Now, the next time it's going to reach this point would be here. And that's why you call it a period, because it's going to go through one 360-degree change from here to here. Agree? Just to give you context, correct? Now, the angular change, omega t, would be equal to 2 pi radians, wouldn't it, class? Right? I'm just showing you one thing. From here to here, we would have an angular change of 2 pi. Do you agree? If you go through a cycle of anything, it's 2 pi, correct? So 2 pi radians would be equal to omega, right, times the period t. Do you agree with me, class? Omega is the radian frequency. T is the period by definition, correct? And therefore, t would be equal to 2 pi. You don't need this. It's just supplemental. Divided by what? Omega. Or it would be 2 pi divided by 2 pi f, or it's simply period is 1 over f. And that's just to put some context on what I'm about to say. Okay. Now, next, we're talking about AC things. I have to do this. I'm doing this because it's going to be so very useful shortly, and you're going to see why. How many remember the name Euler, like Euler's laws? Anybody? It's spelled E-U-L-E-R-S, Eulers. How many do? 1, 2, 3. Got a spattering of hands. Some people don't. You'd be surprised in electrical engineering, in my into sophomore, beginning of junior level courses, how many people don't remember this? Apparently, the professor that showed you this didn't think it was significant. But this is very important. These are forms of Euler's law. So write these down, and you're going to see why it's so important in a second. It's really identities. Now, the first one I like is this. It's E, that's E, like base E, to the J theta. Theta is just an angle, is actually equal to cosine of theta plus J sine of theta. How many remember seeing that? It's Euler's identity, one of many. Guys, MEs, you use this thing daily. I know you guys. I think you're holding out on me. How many, come on, how many have seen this? It's Euler's law. You get this in high school, right? Kind of, sort of, not that one. I didn't see that one, Dr. Baginski. I seen the formula wasn't theta, it was omega t. Well, you got the idea, right? Theta, omega t, whatever form you saw something with an exponential equal to 2 trig functions. Now, what is J generally? Can anybody tell me? The symbol J is throughout engineering. It has a very unique meaning.
Do you mean the imaginary number?
That's right. J, yeah, in math, they use I. If you saw an I in mathematics, we don't use that in engineering, electrical engineering, especially because I is unique and it's saved for indicating current. Do you understand that? So we use J, but J or I is equal to the square root of -1. Do you all remember that? It's called an imaginary number, right? How many have heard of imaginary numbers? You've gone through calculus, you have got to have been exposed to that. All right, good. Thank you very much for responding. And next, if we have that, that's what this J is. Now, I want to give you a little more insight in this if you haven't had. I'm going to give you the other two identities. This is the primary one. There's two other identities, and they can come from this. The cosine of theta is equal to, now this is important, cosine of theta is e to the j theta plus e to the minus j theta over 2. How many have seen that one?
It's a little out of focus.
Oh, thank you. Thank you so much. How many have seen that one? Cosine theta is equal to e to the j theta plus e to the minus j theta over 2. Not a soul for real. In math, you use this all the time. In calculus, I believe you do, unless they're calling this something else. But the cosine is still a cosine, I hope. All right, now, what else? There's another one, the sine of theta. That's the trigonometric function sine of theta is equal to e to the j theta. Go look this up if you don't believe me. Minus j theta over 2j. Engineering is steeped with these type of equations. Anybody remember that one? Gabriel, J is equal to the square root of -1. It's like I in math, okay? Can you all understand me when I'm talking? Am I going? Is there any kind of lag or anything? I mean, if you can understand me, give me a thumbs up so I understand. Okay? And if there is a lag, if there is a problem, please let me know.
I'm not quite following what you're writing with E. Is that E to the IG?
This is e to the superscript j theta minus e to the minus j theta. Are you on a computer, James?
I am.
If you can open up any kind of browser and just type in Euler's identity, spelled E-U-L-E-R-S, and then identity, you'll see it.
All right, thank you.
Sure. Okay, now those are the three basic ones. This is the one we're going to go for today for a very important reason, okay? I want to make this, I don't mean to rush, but it seems time flies when you're doing Zoom, because I keep asking people if they understand. I'm going to turn the page next, and I know it's out of focus right now. I'm going to try to train myself to look over here, even though I like looking over here to see how you're thinking. It'll be in focus in a second. All right, ready? Everybody? Now, here's why I'm doing it. Normally, if we think of a capacitor, this is a symbol for a capacitor, right? And the best way to describe a capacitor is just two metal plates separated by an insulator. Right, what's an insulator? Well, it's like the stuff that prevents electricity from jumping across wires. When you have an extension cord, it's wrapped in rubber or plastic or something like that to prevent one wire from arcing over to the other. Y'all follow me? That's an insulator. That's what's in between these plates. Now, this is a symbol for a capacitor. And the current through the capacitor, this you draw. And here I slow down. If I take a look at the current into a capacitor, I of t, this is into the capacitor, and it will develop a voltage plus to minus voltage across the capacitor. The relationship between current and voltage, regardless if it's direct current or if it's AC or if it's transient in nature, it's C times the change in voltage is equal to I of t. Does everybody follow me on that? It's C times dV dt is equal to the current I. You'll notice the current is entering the positive terminal where the voltage is measured. Do you all see this, class?
Is that a partial derivative? Or is that
No, I mean, it can be, but generally it's a complete derivative.
I was going to read it.
I mean, it could be, but that's really going in the wrong direction. We're going to like graduate level stuff. Okay, it's a simple derivative. Let me give you an example so we know. Suppose I did this. If I just had plus to minus 10 times the sine of 30t, all right, as a voltage right here, this is V of t. And I had a capacitor here. All right, and say the capacitor was 1 microfarad. What's the symbol micro imply, class, anybody?
10 to the minus 6.
Does everybody hear him, class? Can you all hear him? 10 to the minus 6. It's important you understand. Micro is a symbol we use. We use small m for milli, 10 to the minus third. We use small or script n for nano, 10 to the minus ninth. Small script p for pico, 10 to the minus 12th. And I'll spend more time on that later. But microfarad is something you'll see over and over again. Well, if I have that and I asked for the current through there, through the capacitor, I of t, well, what would I of t be? It would be the capacitance, right? 10 to the minus 6, right? Times the derivative with respect to t. I know it's a complete derivative. I'm sorry, it's the partial looks. Times what? 10 times sine of 30t, correct? Y'all with me? I just inserted the information I put down into the definition of the current, correct, class? Okay, what's that going to be? I of t would be equal to 10 to the minus 6th, right? That's first. Then this 10 could come out in front, right? The 10 here could come right out in front. Do you agree with me, class? All right, I'm head bob. I mean, come on, really.
What did C equal up above that again?
1 microfarad, that's 10 to the minus 6 farads.
Okay.
Unit of capacitor is farads. I'm sorry, I didn't say that explicitly. I assumed that. Unit of inductance is henries, but we'll spend more time and it'll become very familiar to you, okay? Now, what happens here? What's the derivative of sine of 30t, anyone? Well, isn't it 30, right? And what's the derivative of sine of 30t? It would be 30 times...
My sine of 30t.
I couldn't hear you. Cosine, I hope you said 30t. Do you all agree?
That's what I said, yeah.
All right. Now you can see what happens here. I got 10 times 10 to the minus 6. That's 10 to the minus 5th times 30, which would be 3 times 10 to the minus 4th, right? And it would be times cosine of 30t. Correct, class? That would be an example. Agreed? Now, let me show you the difficulty in solving generally for the current, and then I'll show you the solution. And you're going to like it, I hope. All right. Now let me go down here. Now, when you have a circuit, and please be attentive here. When you have a circuit, you're going to have some voltage source. These are going to be time-varying voltage sources, like 10 cosine omega t, stuff like this. You're going to have a V of t here, some source voltage. Then you're going to have probably a resistance, R. Don't worry about the value. And here, if I put a capacitor here, right? Now, I said that the current through here, I of t, would be equal to C times dV dt, correct? Now that's the voltage on the capacitor, by the way, right? And call that value C. Y'all follow me what I'm doing? I'm only going to establish the difficulty. All right, now listen to me. Now suppose I wanted this voltage, plus to minus the V here, VC of t. I wanted to know what that was for any V of t. You could make V of t at 10 sine, 10 cosine, doesn't matter. What would you have to do? Let me give you the answer and then I'll show you the difficulty. You all know that's the current through here, correct? It's C times dV dt, and this is what we're looking for, right? We're looking for VC of t, correct, class? Right? So if that's the current, what would the voltage be here across that resistor? It would be the current, C dV dt, times the resistance, right? So this voltage would be what? C times R times the derivative of VC of t with respect to t, correct? Now I'm going to do something. Suppose I make this V of t 10 times cosine of 30t, just so you can appreciate what I'm up to. Y'all follow me? And make it volts. Now follow me. Now, if I wanted to know what VC of t is, and some of you are pretty good at differential equations, so you see what I'm up to. I would go around a loop, wouldn't I? I would say the increase of the voltage here, 10, you don't need to write this down if you don't want to, 10 times cosine of 30t, right? And then it would be a voltage drop of minus C times R, whatever they are, times d VC of t dt. And then it would be what? Just minus VC of t equals 0. Do you all agree with me? I simply sum the voltage drops around a closed loop. How many see this, right? I mean, just a head bob, a thumbs up. Any information is more than no information. Y'all see it? Even I don't know. That helps. Y'all with me? What don't you see, James? You're wobbling your head in the wrong direction. You can't. I got to unmute yourself. Unmute.
Sorry. The middle part that you wrote for the resistor, I'm having trouble reading that.
Oh, the current is equal to C dV dt, right? VC of t?
Yeah.
All right, well, that current flows through all elements because it's series, doesn't it?
Yes.
And therefore, the voltage across that resistor would be that current times the resistance, isn't it?
Ah, I see.
Are y'all with me? I'm going to make a point here. It's not essential. Now, y'all see this right here. Here, we could take this to the other side, right? I'm not going to do this. But what do we have here, class? There's something you've been exposed to and may have hated because you have to use integrating factors sometimes. Anybody? Or Laplace transforms. A differential equation, right? What have you learned about differential equations? They can be irritating because of the possible solutions due to what's called the forcing function, what the voltage V of t is, right? Now here's the grand thing that you're going to learn. We're going to be doing AC or steady state continuous frequency circuits. Now, AC means this is only a cosine or the sine, and here's where it gets nice. Are you ready? Now pay attention to this part, and I only got 10 minutes, and I'm going to try to shoehorn this in, but you're gonna thank me. Believe me, you don't want to solve differential equations all the time. Not with systems of equations. MEs do this stuff, EEs do it. One thing we learn is if we can avoid it, we do. It takes much time and it's irritating. So what we do is this. We say for any given system at all, doesn't matter what it is, as long as it's a linear time invariant system. Now I say that it means circuits made up with resistors, capacitors, and inductors, and more on capacitors and inductors in a bit. But you all understand I'm talking about not nonlinear circuits like diodes and things like that. And most people have an appreciation for it. If I put a voltage source in here.
Can you move the paper up?
Yeah, yes, thank you. If I put a voltage source in here, that's a sine or a cosine, it doesn't matter what it is. If I put a voltage source in here, plus or minus, say a cosine of omega naught t, then my output here will vary at that frequency. The output will have some scaled value. If it's a voltage I'm after, it'll be some A times the scale factor S, and it will be times cosine of omega naught t plus a phase angle. Now, I'm not going to prove that today, but what I'm telling you, if this varies with time and has a frequency omega naught t, the output of any linear system at any point will vary at that same frequency or have the cosine of omega naught t variation with a possible phase angle, and it will be scaled. It may be greater or less than. Do you all follow me on that? That's for a linear system. How many have heard something like that before? And, you know, if you have a constant frequency exciting something, then all possible solution or all possible, I guess, windows into the behavior of the circuit or the system will vary at that frequency. And that's important to note. Now, here's the beautiful thing. If we have a system here, I can say that this would be true. And I hope I say this right. If I have or I'm going to put the source, and I hope I do this in a way that doesn't confuse you. If I say my source voltage Vs of t is some real part cosine of omega t plus an imaginary part j sine of omega t. All right, so now I have a real and an imaginary part of the input voltage, and that's going to go here. And I have my system. You don't have to draw it like I'm drawing it. And I'm looking at a possible output right here. And this is going to be V out of t. Well, V out of t will have some scaled replica of the input. You'll notice I only had one here as the coefficient. It would be some S times cosine of omega t plus a phase angle plus JS times sine of omega t plus a phase angle. Now, the only thing I'm...
The camera's a little out of focus.
Thank you. Let me explain what I'm doing. Here's the input. I, on purpose, didn't put an A there. I just made it 1. I'm putting this into a linear time invariant system. My output right here will just be, that S just represents any constant. Could be 0, could be 5, could be J5. Doesn't matter. It's a scaled replica of this times a cosine of omega t, where omega would be the same, plus a possible phase change. And the imaginary part would be this. Do you all follow me? Now listen carefully. What that means is this. Well, if I know that, if I just want the system's response to the real part, if my input is just this, if that's the input, then what I can do is simply take for V out of t, if this is what comes out, and I want just the output for the input being if the input is and I'll do it this way, Vs of t is just the real part of, I better call this Vs prime, of Vs of t. So what I'm saying is if it's only the real part of that, then my output right here, V out prime of t, will just be the real part of this, V out of t. Now I'm going to give you an example and you'll see. Y'all with me? If you just want this response of the system for the cosine, but you've got the response for the cosine and the sine, you just take the real part of the output and you got the response to the cosine. Does that make sense to everybody? Y'all with me on this? You want to see an example? Fine. I don't blame you. So here's my example, and you're going to like it. So instead of solving differential equations when our input is cosine of omega t or sine of omega t, what we do is this. Now, please listen. We go ahead and we say that if we want the input-output relationships for anything, we assume that the input or output will not be represented by a sum of a sine or a cosine or just a cosine or just a sine. What we'll do is have this. We'll have the V of S of t.
Dr. Brzezinski, we have 4 minutes left, and you told us you would tell us about the quiz.
Yeah, all right. On Friday, I'm not going to do a quiz. What I'm going to do this Friday is go over this stuff. I thought I'd get further. And on Monday, you'll probably have the quiz, okay? Hear me?
Okay.
Still,
I
will
will,
we have
gi-
to be on campus Friday?
I will give you much more information about that at Friday's lecture, all right? Okay, because
So
I'm
we'll,
trying,
we'll come in on Monday, most likely.
yeah, and all this will be made known to you on Friday. Is that all right? Because if you do a quiz now, you're not going to be prepared. You have no time to really get through.
So Friday is going to be on Zoom.
Yeah. I mean,
Okay.
if you want an in-person lecture, if you send me a bunch of requests for that, I'll be happy to do it. I know I have people that want that, a whole bunch of you, but just bear with me. Let me get through this lecture first. And believe me, if it's overwhelming, then I'm going to do it. I'll just have class every day on campus like you want. But just anyway, let me get through this. So back to this, what I was dealing with. Here's how we do problems. First thing we do is we say this. We say, if we have a capacitor, now just listen to me carefully, and this will help you. If you have a capacitor, all right? If you think about it, the voltage here, I'm going to use the voltage as a complex number. I'm just going to say it's some V naught e to the j omega t is going to be this source voltage. All right. The current I of t is equal to C times dV dt, correct? Now, please follow me on this. Do you agree with that? By definition.
Can you move the paper down?
Yes, thank you very much. It's C times dV dt is by definition the current. Do you agree with that, class? All right, now listen to me. You all agree that this voltage is across that capacitance, right? So that current would be what? That current I of t would be equal to C times the derivative of this with respect to t, which would be what? You see how the j omega would come out in front, right? You would have V naught, right? That's a derivative of this with respect to t. And then you would have e to the j omega t. Can you all see that? That's simply a derivative of this voltage. Now bear with me. You're going to like it. If I take the ratio of the voltage across the capacitor, which is this voltage, if I take a ratio of the voltage across the capacitor to the current through the capacitor, what do we usually term that? The ratio of voltage to current across an element?
Resistance.
Yeah, and now it's something similar. It's an AC resistance. What we call this is the impedance. And this is at a constant frequency. All right. So the ratio of V of t to I of t, well, V of t is going to be just V naught e to the j omega t, and I of t is going to be C times j omega times V naught times e to the j omega t. And the bottom line on this whole thing is labeled as Z. That's the symbol for impedance. Right here. And the impedance of a capacitor is simply 1 over j omega c, and the units are ohms. Now, write that down. And I am out of time. I know I get criticisms that I run over. So at this, I am going to stop. I didn't even get a chance to do what I wanted to. And I am going to cover some additional things. I'm going to ask you to do readings on this. But I want to just add this right now. This is for a capacitor. If it was an inductor, now capacitor is C, inductor is L, then the impedance would be equal to j omega L, and it would be in ohms. And this is at a constant frequency. You all follow me?
What does the subscript C stand for? It's supposed to be an L.
Capacitance.
Okay.
And this would be L.
Okay,
C,
that's what I was asking about.
that's it. That's all. And this is an L, and this is capacitance. This is a C. Now, I want to tell you why this is so important. If you need to go, go. But here's a beautiful thing. When we're solving circuits, you're not going to solve differential equations. You're going to solve algebraic equations. Here's how easy it's going to be. And I'm sorry I didn't get there. If I had this, just listen to me carefully so you'll see the beauty in this and where I was going. Let me just turn the page. And you don't have to stay. All right, if you want to go, go, but this is the beautiful thing. So, and you'll get this, by the way, in your FE exam, Fundamentals of Engineering. You'll get it at job interviews too, probably, some version of it. If you have something that is 10 times cosine of 30t volts right there, and you have a resistance of 10 ohms, and then you have a capacitance here of, say, 2 millifarads, and they want the voltage here. I'm going to show you. First, I'm going to say they want the current here. They want I as a function of t, and they want the voltage here. V out as a function of t. I want you to just listen to me. You don't solve that problem. What you do is this. You take this and you know cosine of 30t is just a real part of e to the j omega 30t. So we make the voltage source here 10 times e to the j omega, 10 times e to the j 30t. We're going to suppress that 30t in 1 second. This is the voltage source right here. The resistance stays at 10 ohms. And then we make this an AC resistance. I hope you follow me. We make that an AC resistance. And the AC resistance is just going to be the capacitance, 1 over the capacitance times j omega. So it's 1 over j. Omega is 30, right? And then times C, which is 2 microfarads. Micro is 10 to the minus third, so it's really 1,000 divided by that, isn't it? Y'all, I'm trying, I mean, not micro, millifarads. Milli is 10 to the minus third. 1 over that would be 1,000 on top. Do you agree with that?
Wait, how did you get that again? That
Milli.
J30?
All right, remember, I'm going to go over this on Monday. And I know I hear people jumping on. Remember when I said this was true for a capacitor? Who asked?
Yes.
Okay, that's 1 over j omega c. Now, what is omega? When I look here, omega is the coefficient of t inside the cosine, isn't it?
Mm-hmm.
All right, so it's 1 over j omega 30 times c. Well, c is 2 millifarads. That's 2 times 10 to the minus third, and 2 over 10 to the minus third, or 1 over 10 to the minus third is just 1,000, right?
You said that's equal to the impedance?
Yep.
Okay.
That's the same thing in ohms. And here's the beautiful thing. Now, I better almost stop there. But now if I want this current, well, do you have a voltage? Yes, right? That's the voltage. Do you have the impedance? I can add this plus this and just divide it into that. On Monday, I'm going to go through a bunch of examples.
You can find the current with that.
Yeah, and right now I can see that there are questions that I want to answer that we're over. And I really don't want to have a whole bunch of hate mail from people that I had to go and I don't have time to listen to you. I got a couple of people that, man, they lambasted me. Oh, you said stuff and that wasn't an office hour. That was a learning session. And they're right in a sense. They are right that I should try to shoehorn all this stuff in. But it's more difficult with Zoom to get it all in time. I'll do this on Friday. Now, I'm going to tell you right now, I'll give you some stuff to look at, but you're going to love this stuff because the only thing I'm not even going to bother with this. If this is right here, that thing just changes at 10 at an angle of 0 degrees. I don't know how much.
We can't see the original circle.
Yeah. If this is the original, we take this whole thing and we just put 10 down here, the coefficient. There's no angle here, so it's just at 0 degrees. We assume it's at the frequency, and I'll do this on Friday. I put in the resistance here and I put in this. Now, what is that going to be? How many know what 1 over j is? Anybody? In terms of a numerical value.
Is that j to the minus 1?
It's just minus j. And I'll spend more time on that. So this would just be equal to minus j over or times 1,000 over 60. or it would be what, 100 over 6, right? Or it would be 20, wouldn't it? Or so. Yeah. No.
No, it's like 16.67.
Yeah, it is.
something
It's a
like
weird 16 points. Anyway, the bottom line is this has got an imaginary value. To get this current, you would just take 10 divided by 10 plus J 16.6, and you'll get the real and imaginary part. On Friday, I'm going to go through example after example on how simple this is and how to go from the time to the frequency domain and vice versa for steady state for constant frequency. I didn't get there today, and I apologize. Usually I go through linear systems with you, what means it's tough on Zoom to do this because I don't have a blackboard. All right, now general questions, anything?
For the makeup quiz, I got to figure out a way to prove my COVID. I might be able to call them and have them send me a form or something. But the only
Just
way I get my positive test is they call me like 4 days later.
Just do me a favor, call Fred Cam or get a hold of Fred Cam. And Dr. Fred Cam, you see his email there. Tell him you're in my class. You got a dilemma, and he'll deal with you. He'll either get some staff member to deal with it. Now, here's the deal. I'm going to set this up when people who missed the quiz on Friday, the quiz, on last Friday and have a valid COVID excuse. When they have all this stuff and they're over it, then we'll set it up. We're probably going to have 10 people or more take it. Now, I'll set all this up, but it's in my grader will help me. But it's got to be when everybody's clear, because I'm not going to write 100 different makeups, basically.
Yeah, yes, sir.
It's going to be
I
one
understand.
makeup. It's going to grab them all. And if you don't take the makeup, then I'll just take your final exam score and replace the quiz grade with that, because it's going to get too ridiculous.
Thank you. Thank you.
Now, that said, I got to ask you this. Anything about what we covered today during the class time or anything from prior lectures at all?
I need to like look back over what we learned in class. I just got to get my head wrapped around it more. But I mean, it's the first time I really saw it in a while, so that makes sense.
Well, the new stuff, what I'm going to do is give you some concrete examples that you can look at. You can see, this is the time domain form. Here's what it is when we do this thing in the frequency domain and how we solve it. Then here's how we go back to the time. You see 4 or 5 of these, you'll see it. Engineers in general are very bright, very capable. You'll be able to see patterns and things like that. Any other questions? I'm specifically thinking about Thevenin, because you're going to use Thevenin, you're going to use Norton, you're going to use Nodal, you're going to use Mesh all the time from here on out. And it gets more complicated because you're going to have complex numbers, real and imaginary parts. And you're going to have some other things happening too. Anything at all?
Can you go over what Norton's is again?
Yeah, I can. Actually, what is it Norton? You remember source transforms? That's another thing to cover. What does a source transform say? If I have a voltage, and I'm going to put a real voltage here, 10 volts, right? And if I had 5 ohms, and here's the 2 terminals. Now that's a source. It's a voltage source in series with resistance, right?
Mhm.
What does that become according to source transforms?
A current in parallel with a resistance.
What is a current though? It's the short circuit current, right?
Yeah.
So what would you do? You put a short there, right? And then you would look for this current. That's I short circuit, right?
Mhm.
Which would be what? 2 amps, right?
Mhm.
And then it would be in parallel with that 5 ohm, right? Now this isn't truly Norton's theorem, but what this says is between these 2 terminals and these 2 terminals, the response of any element you put across them will be identical. There is no effective difference in this circuit and this circuit in terms of the response any element will have. Do y'all follow me? And that's source transforms. Now, you asked about specifically Norton. And here's the difference in Norton. If you really wanted to do it properly. Instead of getting an open circuit, when you had a standard circuit like this, and here's the component that we remove the component, say we have RL was there, okay, and that's plus and minus. Your first thing would be instead of finding VOC, the open circuit voltage, the way you do with Thevenin, you would find short circuit current. So the first thing you would do is find I short circuit. You put a short there and find that. Then the second thing you would do is find R Thevenin, which would be the same thing. And then you would assemble the circuit. You would put I short circuit here. You would put R Thevenin here. And then you would replace the load, R load, whatever it was. Follow me? So you would get your short circuit right here instead of the open circuit voltage. Who asked that question?
I did.
Does that answer your question, Brooke?
Yes, thank you.
All right. On this Friday, I'm going to cover this. I would really encourage you to be online and aware, because this stuff is going to get complicated if you're not. I'll make it as simple as I can. I'll give you examples, but I want to warn you about something. If you're not familiar with Euler's identities and imaginary numbers, now's the time to tune in and stay sharp, because see, this stuff will get really confusing if you don't stay tuned and do the homework. And unfortunately, I didn't get where I was wanting to go. In his book, this is an office hour. Anyway, while I'm showing this, does anybody have any information for the good of the group about anything going on in Auburn that would be of benefit for the group? Anything at all, or anything in the vicinity? I saw this up to 598 cases of COVID in the last week, right? According to what was officially announced, which is a little troubling. Let me try to do something. I'm trying to use your, one of the natural things, and they're right about this, is asking, well, why did we even buy the book if we're not going to use it? Well, you're going to use it, but not for that stuff that I showed you before, because in my opinion, it is, it's easier for me to do it my way than try to go through his book, because he assumes too much. Now, in his book, if you go to page 22 of his book, can you all see this okay? That's just the book you bought. You go to page 22, he's got Euler's identity right there, right? You all see it? I'm getting worried. I see one head. Everybody else says, I don't know what can you all see that okay?
Yes, I can see it.
This is Euler's identity. Now he goes ahead and he says, well, what if this is multiplied by Z? Well, Z is something that is the impedance I was talking about. And then it would be just Z times the cosine plus JZ times the sine, which is kind of intuitive to me. All right. Now the magnitude of that, listen to me now. What's the magnitude of this? Just take a look at that orange line. What's the magnitude of this? Well, it would be what? The square root of cosine squared plus sine squared, right? Because that's a real and imaginary part.
Tangent or something?
Well, no, that's the angle between them. Would be the tangent is the opposite over the adjacent, and the inverse with that. But if you look at this, what's the magnitude? And this is the beautiful thing. The magnitude is 1. E to the j theta is 1 at an angle of theta. So if you look up here, and I'm going to write in this book, this will always have a length of 1. This is the angle theta. So when you have e to the j theta, you have 1 at a certain angle from the real axis. This is the imaginary axis, or the j-axis. Do you all see that? So if you look for the projection on the real axis, it would be what? Cosine of theta. If you looked at the projection on the imaginary, it would be sine theta. Can you see this, class? Everybody? Now, if you're not familiar, look at this. It'll make perfect sense. When I have e to the j theta down here, that's just 1 at the angle theta measured from the x-axis counterclockwise. So this is theta. And from there, you can get all the proofs you want. Well, if I want to know what would equal that, well, if I take the real part of that, it's just cosine of theta would be this part x, plus j sine theta would be y, correct? Do y'all see this? Have you seen this before? Anybody? Thumbs up, head bob? No, I'm actually shocked. They usually do this in your mathematics courses and calculus for sure. You should have seen some of this. Or maybe you don't remember. But you should have all been exposed to this. I can only speak for Auburn physics and Auburn calculus. I don't know if you go into Southern Union or someplace like that. I have no idea what you've seen. But normally this is something part of the curriculum. Euler's laws are used extensively. Okay. He shows us on page 22. In fact, he gives you some problems on page 23, simple examples of magnitude and angle. Like if you have 3 plus j4, convert it to a polar number. Well, a polar number is magnitude and angle. Do you all remember that? Polar numbers? Right, yeah. Magnitude and angle. Magnitude of anything where you have a real and imaginary is the square root of the real plus the imaginary. Those 3 squared plus 4 squared, square root is what? Square root of 9 and 16, which is what? 25, square root of that is 5, right? So the magnitude is 5, and that's the magic triangle. Remember 3, 4, 5, the hypotenuse, right? The angle would be what? The inverse tangent of the opposite 4 over the adjacent 3, or the imaginary over the real. And the angle you would get is 53.1 degrees, or 0.9273 radians. And this is the way an angle in polar is rendered, and I'll spend time on that. And I am aware I'm talking fast, but the reason I'm doing this is because this stuff is something you've been exposed to, but you need to re-expose yourself and get familiar with it. Now, in his book, I don't spend a lot of time on this because your calculators do this. In a nutshell, he goes through, and this is the reason I don't do his, because when he starts his book, he starts using differential equations for everything. And you don't need differential equations for what I've showed you up to this point with resistors, capacitors, and with resistors and power sources. And Kirchhoff's laws don't need to be written in a form that's a bit abstract. Summation signs are great in general for mathematical proofs, but it's better to see problems worked in their fullness. He shows you the concept of power and energy, things that in physics you've had before on page 37. I don't spend a lot of time on that. I show you how it's used specifically in the cases we're going to get to when we deal with power. Then he goes through this. Right off the bat, he goes through the differential equations that I'm just starting. And that I save for this time after we get circuits out of the way, the basic forms. And he goes through the differential equations that we're not going to solve that way. And then he starts in on this stuff. Now, some of you, if you look here, are going to say, well, we did some of it, but we didn't do a lot of it. Come Friday and Monday, you're going to see we're going to do a whole bunch of it, and you won't be confused. I don't know what the other class is doing. I have a feeling they've already gone through capacitors and inductors in steady state. I have a feeling they've also probably not done due diligence with mesh and nodal, and that's where I spend most of my time because I know how valuable that is. Does anybody know where the courses, the other courses are? I mean, the other sections of this course, what they're doing? Nobody? Nobody. Usually people are, they're talking amongst each other. When I teach a section of 3810 and Irwin does, they're always finding out where Irwin was and where I am. And usually I'm a little bit ahead of Dave Irwin until the end, and then he'll get ahead of me. All right, any other questions? Now, by the way, did Friday's lecture make sense to you when I was there? This was the in-person lecture delivered before the quiz.
Is there any way for people that had COVID to see that lecture?
I hope so. Isn't it up? Should have been recorded. That lecture should have been recorded and online. Is it online or not, guys? You don't know. I assume it's there, but I can check. It should be there, John. You have COVID right now?
Not anymore. I just ended my
alright.
quarantine.
That's all right. I mean, but you're over a fever and stuff. Does anybody here that I'm looking at have COVID-19 active? All right, for the record and off the record, if you know of anybody in the class that has it and needs help, either getting food or something, then I suggest you help them. And if you can't, let me know and I'll find a way to help them, because this is a crazy time. I mean, this is unlike anything else. I mean, I've heard all sorts of horror stories of people being so tired they couldn't do a thing, and literally they couldn't even drive. So if that's the case with any of you, and I hope it's not, let me know and I'll find a way to, we'll find a way to respond to you. Now, are you guys pretty much up to date with at least the material before this lecture, class?
Yes.
Okay.
And it doesn't seem like the lecture from Friday is posted anywhere.
Tell you
Yeah.
what, I'll take a look. It should have been, because it was recorded on Zoom, but it won't be the quiz. It'll just be the lecture. Let me stop sharing. I got
It
it.
looks like the last lecture that was posted was from the 2nd of September.
Well, that's a shame, because we recorded that one. Let me take a quick look. I mean, that was recording. I know that.
Was there any new material that was covered Friday, or was it just review?
Just review.
Yeah, just review.
It was answering questions, specific questions. Is really what it was.
Okay.
And but that's not a good thing when see, this Zoom stuff is supposed to be automatic when I jump on Zoom. Let me see if I can take a look at it. I thought it was mailed that. Let me see here. We had one problem where it just recorded the audio. Zoom issue.
If it was just reviewed, then I can probably get the notes from somebody else.
Yeah,
I
but
think I asked a question transform, and then we ended up doing mesh also, but I think that was the only problem that we did. Yeah, we did the transform problem, and then you explained about the mesh with the eyes, how that could be included, and then we had the quiz.
yeah, but really, what I'm looking for this. Bear with me here. I'm trying to. There have been some problems with Canvas, I know this, and somehow Zoom's had a few problems too. I never had any problems with Zoom when I let the students prior to this in my spring and summer courses record it and post it on YouTube, not in that cloud server, but on YouTube. And that way they could access it anytime forever, because it's never coming down. And I prefer doing that. If I can get permission to, I will. I'm still waiting on some stuff. I'm checking right now on what you just asked, John. All right, here's Zoom. Only 4 people left. Jessica. Jessica, are you a tennis fan too?
I'm sorry?
Are you watching the US Open Tennis Championship?
No.
Okay. a lot of the people, well, one in particular from South America, from Brazil, as it was well, I'm sorry, not Brazil. It was a country just north of Brazil. A girl who played in the European tour. She was a brilliant engineer here, and she loved tennis, and she would be watching. A lot of people, I think, in Brazil play tennis, from what I was told.
I like watching more soccer ones.
Soccer, yeah.
That's what they play the most.
And you're right about that. All right, I got September 4th. Whoever said that, yeah, the 4th's up. Who said they couldn't get it?
I did. I mean, for me, it's only showing like the second.
Friday,
can go to-
September.
I can go to previous meetings and see that there was a meeting, but it doesn't show that it
You go on a Zoom?
cloud recordings.
Oh, is that right? I'm clicking on it right now.
I mean, I refreshed my page and it's still showing just a second.
Previous meetings was Friday, September 4th.
hmm
All right.
And then I went to cloud recordings and it's not there.
Oh, here's the report. It's 31 minutes. Let me just check this. I'm glad you said that. By God, you're right. Unless it's down at the bottom. No. I don't know what happened. Because previous meeting, September 4th. Well, it makes no sense. I don't see recording either. Fortunately, it's just a basic review, I believe.
Okay.
Hey, I'll tell you what. If any of you remind me, I will make somebody else a co-host. They can record it and put it on YouTube. Jessica, would you like to do that?
Yes.
I mean, I'm volunteering you because you're always there and I recognize your voice, but what you can do is record this and just put it on YouTube. Now, in the past, my summer course and my spring course, we did that. And the nice thing about that, there's not a problem. We never had a problem with recording. You can go back on all my lectures in 3810 and radar and stuff like this or whatever it was, and they can find, they're all out there. YouTube does not like eliminate prior material. There's stuff on YouTube that I got recorded on from 2016, 2014, 2010, I think, or 11. So that's a permanent record. As far as I know, YouTube doesn't do anything. And if you want to do that, that would be great. Okay.
Okay, I'll do that. I just have to be the co-host, so I'm able to record it.
And the very first thing you do is send me an email or say something that please make me the co-host because I'm liable to forget. Okay.
All right, sir.
All right. Did you have any other questions, John?
I don't think so.
Jessica, do you have any other questions?
If you want to do like a project of like creating a circuit thing at home with some wires, like what are the materials you could buy? Light bulb, something with the light bulb, if it's possible.
I'll level with you. You want to find out stuff. Wait until we get done with capacitors and inductors. and maybe get an electric motor, look on YouTube. YouTube, I'm telling you, I did a railgun project years ago, did a couple of them for senior designs. Then it was right after 9/11, and the Department of Homeland Security shut that whole thing down. But the thing I can tell you was that there's even a data record of that in 2002 and 3 and 4, was at least. YouTube is the outlet for everybody that likes to showcase what they've done. And circuits, there's tons of stuff out there. Trust me on this one. I'll be happy to show you some.
All right. Thank you.
By the way, Gong Yijin, do you have any questions for me? Oh. I don't know who this person is, Christina. Is this a tennis player or something? I've got a question on chat. I'm actually going to look this person up. I don't know who this is. It is a tennis player, I think. Oh, soccer player. Never mind. So,
Oh,
Jessica,
yeah.
you know who it is.
Cristiano Ronaldo. He's from Portugal. He's like one of the biggest soccer player. He's very famous, just like Messi. Yeah, I think he won a lot of championships.
I can see he's famous. I'm not a soccer person. But I know a lot of people are from South America and Europe. They're bananas about soccer. Germans especially, that I've known. And I guess guys from Brazil too. Yeah, you won. Wait, Germany beat you one time and you were embarrassed, and Brazil went bananas. And after, I remember that for the World Cup. Long ago, it seems like. All right. I don't think we have any other problem or any other questions right now, and I'll get this other stuff to you, okay?
All right. Thank you.
All right. All right. We'll talk on Friday, okay?
All right.
All right. Take care. Bye-bye.
Bye.